Okay, we begin the PowerPoint presentation here. This is our team. We have 3 postdoc and 1 professor. The team is led by Professor Peng Hui. Regarding the background, we focus on the pain points on the smart glasses in this presentation. Low-end smart glasses have limited hardware configurations, which presents challenging issues such as limited display size, small input interface, limited computational power, and short battery life. So running a consuming algorithm on smart glasses will significantly hurt the sustainability. And we have no easy way to operate the smart glasses because the interface is very small and voice input is sometimes unreliable and external controller or trackpad are not very user-friendly. The existing interface and interaction methods on smart glasses, we have the discussion here. For example, Google Glass has a trackpad on the head position, enabling swipe-based gesture. This makes a card-based operation system on Google Glass and swipe-based gesture to swipe between cards. But this limits the flexibility of the operating system. And on Mac case, we have a normal operating system, but it has a trackpad on the button. And this design, due to the form size of the smart glasses, make the jumpy cursor and also introduce interaction difficulties. And on the Epson smart glasses, it has an external controller, but a hand is occupied, so it limits the mobility. And the Mac case also introduced a portable keyboard. Yes, it is easy to carry, but it enforces the user to sit down and sacrificing the mobility. So we have an introduction video here. This is a swipe-based operations on the card-based system on Google Glass and relies on the voice commands. However, it cannot do some special word input. Next, this is the Mac case, but it is quite difficult to use, and operation here is 16 times faster. And the user needs some attempts to adjust the cursor position. So we see the key challenge in the interaction side, and on the constraint side, we also have the efficiency problem. Smart glasses has 2 key limitations: low computation power, only 1 GHz clock speed on the low-end smart glasses, and low battery life, like 1 to 3 hour usage. The battery will use up quickly if we run some intensive computation tasks. And also, we need to best utilize the limited computation power. So you may question why efficiency is very important. Here is the motivation. And we try to compare the smart glasses, the capacity of smart glasses with the computers in 2000, where Intel claims it was the first to market with a 1 GHz processor. And you see the configuration here. Google Glass has the similar clock speed with limited memory capacity. As such, people are wearing the 20 years ago computers on their head. So we present our system solution, UbiPoint. And UbiPoint try to map with the user's fingertips and the system pointers for object manipulation, such as pointing and selecting. Here is the demonstration video. The user points at the starter button and do the mid-air taps and click into the browser and start typing SimLab like what it can not be done on the Google Glass with voice input, SimLab, a special word, which is the name of our laboratory. In the system solution of UbiPoint, we have two modes for the interaction. The first one is freehand mode. It designs for handling scenario requiring multiple input options. And our video just shows the freehand interactions in the test entry scenario, and the point and select operation in the first row of the figure here this is the illustration. And the user first point to a target in 1B and then do the hold at this position for around 500 milliseconds, and then do the mid-air tap to do the to complete the process. And also we decide the corner and edge as a strategy to record some predefined gesture. Because in mid-air, we cannot precisely define where is the endpoint of the gesture, this problem is named as Midas problem. And so for corner case, first we ask the user to point at the middle of the interface and then hold for 500 milliseconds and then select an edge and swipe to the edge. Then the gesture complete. And this can map to one of the command line going to the previous page in the web browser. And another one, and another strategy is corner strategy. From one corner, hold 500 milliseconds and move to another corner for one gesture. And next mode is the fast repetitive mode, which enable user to focus on multiple select and click operation in a focused task, like character inputs. And it makes the pointing gesture with the hardware touch interface on the frame of on the body of the smart glasses. So the pointer will still follow the hand of the user and point to somewhere. When the user want to select this character key, the user tap on the body of smart glasses, which is a touch sensitive interface. So we leverage the highly responsive hardware interface to support the task require repetitive and fast input. To make the two interaction modes feasible, we propose a fingertip detection algorithm using a graph-based approach. In the image segmentation, we employ the HSV threshold value divided by Asian and Caucasian skin. In the HSV histogram of the hand here, we can see a peak here in the hand, for the hand, between 0 to 20 here. And the peak saturation, the green one, around 115. And a value, the red one here is 200. And here is the algorithm, the fingertip detection mechanism in UbiPoint. I described the high-level description here. After the image segmentation, we find the pixel with the skin color, and divide the vertex in our arborescence graph, DA. And then we employ a sliding window to search the vertex with a recursive breadth first search. So in this process, we can identify the solution, which means the detection point of the fingertip, with the maximum number of nodes or vertex in the DA. And here is the illustration, the finger here. And from the leftmost, we have the captured hand image. And then we do the image processing, segmentation. And we use our graph base to do the optimization and search upward. And we get the fingertip detection and this one has the maximum number of nodes. And then this point will map to the control interface. And here is another showcase when someone behind serve as a disturbance in the background. So UbiPoint works quite well in a noisy environment. So here is the system performance. We have 5 metrics: speed, accuracy, CPU utilization, memory utilization, and energy consumption. And this slide, speed and accuracy. We test UbiPoint frame per second on Mac Gaze and Google Glass, two low-end smart glasses, and Mac Gaze shows an average of around 20 FPS with a minimum of 13 FPS. And Google Glass has around 18 FPS with a minimum of 15 FPS. So overall, our solution is higher than 15 FPS, which exceeding the minimum requirements for seamless interactions. And we also test the accuracy. The pixel errors is less than 7. And for CPU utilization, upper one is Mac Gaze and lower one is Google Glass. And CPU occupation reached 19.5% on Mac Gaze and 35% on Google Glass. And regarding the memory use, the Mac Gaze and Google Glass has reported around 5 to 6 megabytes. And also, we have sufficient CPU capacity from in the perspective of CPU and memory, reserving for other applications. So we can say UbiPoint is lightweight. And also, the final metric is the energy consumption. We run the experiment in 4 conditions: idle, display off, idle, display on. And also we run our illustrated application on UbiPoint. And also we compare the UbiPoint with the camera situation. So we can see, we compare the Fingertip, our illustrated application, with the camera on. There is only a slight difference, around 16% to 40% on Mac Gaze and Google Glass. So you can see the our algorithm is energy efficient. Regarding the user evaluation, we ask the user to do a user test. The first one, we ask user to click on some box. It is a test for target acquisition, point and selection. So our statistic analysis shows that we have the task tool as the baseline, and the Fingertip on Mac Gaze and Google Glass outperforms the baseline. And our analysis also shows that the improvement is around 33%. And the second task is the test entry rate. We measure the test entry rate and the error rate. And the corner position here, we have the setup with the user. And fast repetitive mode, because it has the hardware interface and it is more responsive, so the user can do around 4 words per minute with a standard deviation value of 0.66. And with freehand mode, it is 4 times slower and around 1 word per minute. And error rate, because freehand modes need a lot of mid-air tap and hovering of 500 milliseconds, so freehand mode has higher error rates than the fast repetitive mode. And here's the summary. UbiPoint is responsive, reliable, computational efficient with reasonable energy consumption. And UbiPoint help the user to handle their tasks easier. And before we go to the conclusion, we show 2 application scenarios: killing monster in game, and also a large display standing with the audience. Conclusion: UbiPoint relies on bare-hand mid-air interaction and solve the constraint issue on the smart glasses. And we propose 2 modes: freehand mode, fast repetitive mode. And furthermore, UbiPoint does not rely on the voice command and head movement, so it is more easier to use. And UbiPoint also has a lightweight algorithm. That's it of our presentation. Thank you.